this working? Okay, seems like the Wi-Fi is working, and let's go back to teaching. Okay, so we are talking about linear algebra and Dirac notation. Okay, so last time we stopped here. Okay, so we are seeing inner product. So inner product is a concept that you should probably learn in your linear algebra course. But here, our inner product is a bit different from what you might learn in your sophomore year because we are in complex vector space. So all the coefficients are complex, and it turns out, so if you want the inner product, then you have a coefficients as A, B, C, D, then the inner product is not AC plus BD, but it's this A star C plus B star D, where the star are those stars are the complex conjugate, and this results in that the inner product is not symmetric in its two argument anymore. So V inner product with W is actually the complex conjugate of W inner product with V. And we want this complex conjugation because we want the inner product to still give us the norm of the vector. Okay, so inner product taking square root is still the norm of vector, and the norm of vector is the square root of A absolute value square, B absolute value square, and then we know A absolute value equal to this A times A star. That's why we need a little star here. Okay, so this is inner product, and and with inner product we can define what's orthogonal, just like in usual in the real coefficient, linear algebra. We define orthogonal of two vectors as if the two vectors has inner product 0, then they are orthogonal. And also with inner product we can define the norm of our vector, just like here. Okay, so we can normalize our vector by dividing by dividing the vector with its length, and then we will get a normalized vector. Normalized vector is a vector with length 1, and then we can have a set of vectors that's also normal. That's when all the vector inside the set has length 1. They are unit vector, and also they are orthogonal to each other. That's also normal. And then we can have the concept of orthonormal basis. So orthonormal basis is just a basis that's orthonormal. Okay? And basis is a set of vectors that span the whole vector space and that are independent to each other. Okay, just a quick review. And also, if you have any basis, you can make it orthonormal by applying this grand streaming procedure. And this we will not review. If you don't remember, look up a book. Okay, everyone okay with inner product? If not, then we'll talk about outer product. Okay, and outer product is a concept you probably don't stress too much in your linear algebra course. But with Dirac notation, outer product looks a bit nicer. Okay, so it looks a lot like inner product. So inner product is just this. Let me see this thing here. So V inner product with W will be written like this, and you see it's a bra vector multiplying with a ket vector. And then outer product is quite similar. It's a ket vector multiplying a bra vector. And basically what this gives you is a matrix. So you have a column vector multiplying a row vector, then you will get a matrix. If you think this as a matrix, you will get a matrix. And I guess here we see a stronger example. So more explicit example. So we have phi equal to 1 minus I, and psi equal to minus 1 minus I. Then we can write down this phi vector is 1 minus I, and then this psi I brought vector, then it's this -1, and then this -I become I because we do transpose and conjugate. So this -I conjugate to I, and then we just apply matrix multiplication rule to those two matrices, then we'll get this matrix. So let's do this slowly. So the first row will be 1 multiplying -1, get this -1. 1 times I equal to this I. Then -I times -1 become I. And -I times I become 1. Okay. And yeah, so outer product, simply if you look at the face value, it just gives you a matrix. Okay. And then there is some more linear algebra interpretation you can put on outer product. So you can think V is from some space V and W is some space W. Then this WV will give you a linear transformation that maps from space V to space W, okay, like this. So you see that it's some number. So say you apply this on some other vector V prime in space V, then you will get this value because you have W multiplying V, W multiplying V prime, and V times V prime. You can, so this is basically 3 matrices multiplying together. Then you can do those 2 matrices multiplying together first, and you see that this is actually an inner product in this space V, and so this is just a number V inner product with V prime, and then multiplying W. Okay. Anyway, but this interpretation we will not use too much for now. You can just know outer product give you a matrix, and it has this nice Dirac form notation. Might be a little nicer than your usual notation in linear algebra course. Okay, and then we can also think about the concepts of eigenvalue and eigenvectors. Okay. And here is, I guess, both a review and the notation about eigenvalue and eigenvectors. Okay, so to find eigenvalue and eigenvectors, we start with some matrix A. A is n by n matrix, and for eigenvalue and eigenvector, you want A to be a square matrix. So those 2 dimensions are the same. Okay. And then there are eigenvectors of this matrix A, and there are non-zero n-dimensional vectors V such that they satisfy this equation. Okay, I should have this equation bigger, but this is the most important equation here. So this eigenvector equation is the A multiplying on some vector equal to some number. This number is called eigenvalue, so some lambda V. Multiplying on this V. So basically, if you multiplying this matrix A, or you apply this matrix A on your eigenvector, you get your eigenvector back, but with some constant multiple. Okay. And lambda V is something that depends on your vector, but it's just a number. Okay. So lambda V, this is a complex number now, and its eigenvalue of A correspond to this eigenvector V. So yeah, so this is the eigenvector equation in terms of Dirac notation. And then now we start with a bit of a review on eigenvalue and eigenvector. So you can find, so if you are given a matrix A, how you find eigenvalue and eigenvector is that you first find eigenvalues by solving the characteristic equation. So you solve for determinant of this A minus lambda I equal to 0, where lambdas are the possible eigenvalues. Okay, and yeah, we'll have an example in the next page. But here first we have extra definition about what is I, and I is the identity matrix, and I is the identity matrix of. So here we are a little sloppy about notation. I is the identity matrix for any dimension. So it's this matrix where the diagonals are all 1 and the zeros all other where, and it can be 2 by 2, 3 by 3, or 5 by 5, etc. And yeah, we are just being a little lazy about not writing on the dimension here. Okay, and anyway, let's go back to an example of solving characteristic equation. This you should really learn in, I think, even in high school. But anyway, here we have an example A equal to this 2 minus I 3 I2. Okay, and then we are going to find the null space of some matrices. Okay. Anyways, and that's the notation we use is NOP. And back to solving determinant, so we have A minus lambda I, and it will be this matrix. So just diagonal, you have minus lambda on 3 parts, and you try to see what is determinant. And we skip all the calculation, and we see that this equation has 2 solutions. The solution lambda equal to 3 and lambda equal to 1. Okay, and so those two are your eigenvalues. Then you can calculate the eigenvectors by by finding vectors that correspond to by finding the null space of A minus lambda I for different lambda. Okay, so for lambda equal to 3, you have A minus 3I equal to this minus 1 minus I minus 1. And then you try to find the null space, so the vectors that multiplying with this matrix become 0. And you can do this by either Gaussian elimination, or usually you can do this by just by eyes. You can look at it. So you see a whole bunch of 0 here, and then you see you multiply this with 0, 1, 0 will become 1, 0. And also this minus 1 minus I will give you a vector that is 1, I, etc. Okay, and anyway, you see that the null space is spanned by those two vectors, and then you normalize it. Then we see those two vectors are eigenvectors correspond to this lambda equal to 3. And similarly, for lambda equal to 1, A minus I will equal to this vector. And then you see that this 1 minus I, 1, 0 minus I is the null vector for this matrix. So this is the another eigenvector for A. Okay. So and I guess here we should write BHR. Okay, and so now we find all the eigenvectors of this A matrix, and so okay. And let's do this in reverse order. For lambda equal to 1, the eigenvector is this, if we normalize it, is 1 over square root 2, 1, and minus I. But for lambda equal to 3, then it's a bit more complicated. So we here we list two vectors that's orthogonal to each other. This 1, 0, I, and 0, 1, 0. And but actually, there are infinite number of eigenvectors for lambda equals 3. So because any linear combination of those two vectors is also eigenvector with lambda equals 3. So basically, the span of this whole two-dimensional space spanned by these two vectors are all eigenvectors with lambda equals 3. So actually, we have eigenspace here. And so that's kind of why we spend time to talk about this example, because this is a kind of quite important concept in quantum computing also, is that we have this degeneracy idea. So when we find eigenvalue and eigenvectors of some matrix, sometimes we will have this degeneracy where eigenvalue has more than one eigenvectors corresponding to it. Or to be more precise, we have more than one eigenvector that are linear independent to each other that have the same eigenvalue. Okay. And when this happens, we say this eigenvalue has degeneracy. And yeah, in this example, lambda equals 3 has degeneracy, and then it has a degeneracy of 2, and excuse me, and its eigenvectors are actually more like eigenspace. It's a two-dimensional space. Okay, and any questions so far? No. Okay, eigenvalue and eigenvector. Now let's go to another thing. Okay, we are still on eigenvalue and eigenvector. Your eigenvectors have a nice property, and I guess we should start from here. So matrix is unitarily diagonalizable if it can be written like this. So it's A equal to summation this eigenvalue lambda I and this kth I and bra I. And so basically those i's will be eigenvectors. And well, diagonalizable basically says never mind. Let's just stay here. And here the important part is unitarily, and that means what unitarily means vectors, eigenvectors. But what's hard here, vectors, eigenvectors. But what's hard here is the orthogonal part. Okay. So being unitarily diagonalizable is more than diagonalizable because the eigenvectors are all orthogonal. Okay. And yeah. So then we also have so unitary diagonalizable basically means that all the eigenvectors are orthogonal to each other, and you have a number of eigenvectors same as the dimension of your A. And then if that happens, so here I guess we skip a little bit. If that happens, we also can write A nicely in this Dirac notation. So A will be the sum I lambda I and II. And I guess let's do a bit of example of showing why this notation makes sense. So say, this notation is a bit too simple, but anyway, so A in this term, and say we have another eigenvector, J is eigenvector, and then we have then we want A times J should equal to lambda J times J. And why is that true is because then so quadrant mark is should equal to lambda J times J. Okay. And then why is that satisfied from this notation is because then let's write down, so A equal to sum I lambda I and lambda I and I and then we multiply J here. Okay. And then this thing is equal to sum I lambda I. Okay, then let's write down something. Let's do a little more. And then you see that then here we have this inner product between I and J. And so that's a number. Let's just write this number here, I and J, and I here. Okay. And then here we can use the fact that those vectors I form an orthogonal basis. Okay. And if J is also one of them, then then I is also no basis, then this inner product between I and J is 0 when I not equal to, this thing is 0 if I not equal to J, because those i's are orthogonal to each other. And this is equal to 1 if I equal to J. Okay, so this thing, let's do this part equal to 1 if I equal to J, and 0 if I not equal to J. Okay. Because those as we said, those eigenvectors form an orthogonal basis. Okay. And then this tells us that so we have a fixed A, so we have a fixed J here, and we sum over all I. And but all other I that don't equal to J don't give us any term here, because when I not equal to J, we just get 0 here. Okay. And so this summation only pick out because of this inner product with J. The only non-zero term in this summation is when I equal to J. And so the result we got here is just that when I equal to J, then this term is 1. And I draw this I'm writing this wrong. This should be this I cat here. I cat inherited from here. Okay, hopefully. And yeah, so we see that because of this inner product, I must equal to j. And yeah, and then we got we don't run out of space, but anyway, we got this result. So this lambda I become lambda j, and this I become j. And yeah, so here we see why this expression makes sense, because you multiplying this on eigenvector j, then you get lambda j times j, and this will guarantee. This means that this expression guarantees your eigenvalue eigenvector equation. Okay. Yeah. So this is unitary diagonalizable. Then let's go back to a bit of linear algebra and a theorem that will not prove here. So this is a spatial theorem. Is that, but it's nice to know is that a matrix is unitary diagonalizable if only if A is normal, and A is normal is just this definition. A matrix A is normal if A dagger A equal to A dagger. Okay. If you have arbitrary matrix, those two will not be the same, because you switch the order of multiplication. So because A dagger and A are different matrices usually, and you switch the order of multiplication, then you might have a different result. But anyway, if you satisfy this, it is normal. And we are going to see that a lot of matrices we know are normal. Okay. And okay. Any question? This might get covered in your linear algebra course, but I think it's a bit more advanced part. Okay. And okay, so this is unitarily diagonalizable. And now we talk about different property of matrix. Now we have a unitary matrix. Okay. And unitary matrix, its definition is that matrix is unitary if U dagger U equal to identity. Okay. And yeah, this is pretty straightforward. And let's see an example. So we have U equal to this 1 over square root 2 and 1 I minus I. Then we can calculate U dagger U. So let's write down U dagger. U dagger, we still have this 1 over square root 2. Then we need to transpose and complex conjugate this thing. So this 1 is still 1, and this I minus I become minus I and I here. Okay, and then we multiply original matrix U 1 over square root 2 and 1 I minus I. Okay, and let's see what's this. Then this is 1 over 2, and let's try to see where they are 2, 0, 0, 2. Okay, and so 1 plus 1, 1 times 1 plus minus I times I, and so this 1 plus 1 equal to 2. Then we have 1 times 1 plus minus I times minus I, and minus I times minus I is minus 1. So we have 1 plus minus 1 equal to 0 here. And then this entry we have 1 times 1. We have 1 times 1 plus I times I. And I times I is negative 1. So it's positive 1 plus negative 1 is 0. So also 0 here. And finally we have 1 times, oh sorry, wrong direction. Finally we have, okay, 1 times 1 plus I times minus I, and once again that's 2. Okay, 2. And yeah, so we check that this is identity matrix 1, 0, 0, 1. Okay, so the U we write down here is a unitary matrix. It should be pretty elementary. Okay, and then there are a whole bunch of property of unitary matrix. So first is that U dagger U equal to identity. Then so there are a whole bunch of equivalent definition of unitary. So first one is our definition, and the second one is you can switch the order of this U dagger and the U. So also U dagger U equal to if this is satisfied, then this will also be satisfied. U times U dagger is identity, and then from those two things you can see that unitary matrix will be normal. Okay, and because of those two are equivalent, we see U is normal, then U is unitary diagonalizable, and also its eigenvalues will have norm 1. So basically, eigenvalues has norm 1 means that it will have this form e to the I theta. Okay, where theta is a real number. And the other properties are that the columns of U will form an orthonormal basis, and this is easier to see here. So here the columns of U is 1i and 1 minus i, those two things. Oh, sorry, 1 over square root to 1i and 1 over square root to 1 minus i. And it's easy to check that those two vectors are normalized, and also they are orthogonal to each other. You take inner product between them, it's going to be 0. And also rows of U form an orthogonal basis. So this 1 over square root to 1 1, and 1 over square root to I minus I, they are also orthogonal to each other. This one you are having 1 1 and 1 minus 1. Okay, and they are orthogonal to each other. And then the last property, this is a property that's kind of most important. This is a property. This is why we care a lot about unitary matrix in quantum computation. Is because you preserve inner product. Basically, you preserve the length of your vector. So you have psi phi. You have two different vectors, psi and phi, and with the same dimension. Then you apply unitary on both of them. So you now think about u psi and u phi and their inner product. Then you take the inner product between u psi and u phi, and by our definition of inner product, you take a you take the dagger of this vector, then dagger of this matrix multiplying with this matrix. So we take a dagger of this thing, then remember, let's see, where are we? The dagger thing should be here. So remember we have this AB dagger equal to B dagger, A dagger thing. Okay, and go back to here. So here we have this U psi dagger, then it should be psi dagger and times U dagger. And we know psi dagger equal to ket psi. Okay, sorry, bra psi. So we know ket psi dagger equal to bra psi, and U dagger is just U dagger. So we take a dagger of this thing, it becomes bra psi U, and we multiply with this U phi, and so the inner product is this thing. And now we see nice thing happen. Then we have U dagger U in the middle. And by our definition, we have U dagger U should equal to identity. So you are just have identity matrix inside. And I guess we didn't prove, but it's easy to see that identity matrix times any matrix is itself. So identity is nothing. So we just have a psi inner product with phi here. Okay. And so here is a proof that any unitary matrix preserve the inner product between two vectors, and by preserve I mean U psi inner product equal to U phi inner product. And so this in particular, this means that the unitary matrix will preserve norm, because remember norms are defined by inner product, right? Norm of your matrix is square root of inner product with itself. Okay? And because the inner product with yourself is also preserved when you act on a unitary matrix, so we know that for OV and the unitary U is UV, norm of UV equal to norm of V. And yeah, this is important for us, because when we do transformation on quantum state, we want its length to stay normalized. Okay, this is a unitary matrix. Any question? Not? Okay, then we back to unitary diagonalizable. And now we back to say why why unitary diagonalizable is called unitary diagonalizable, because it's diagonalizable with unitary matrix. Okay, so matrix A is unitary diagonalizable if you can write it as three matrices multiplying together. So unitary matrix U then times the diagonal matrix. So this is the diagonalizable part. So you become a diagonal matrix, and U dagger. So this dagger of this unitary. And so I guess if you want to write this in more diagonalizable notation, then we have D on this part equal to U dagger A U. Okay, so we're just moving things to other side. So apply U dagger on both sides, on the left side of both sides, and multiplying U on the right side of both sides, then you will get this equation. And this is diagonalizing your matrix, so you multiply U dagger, then on the right hand, and then multiply U on left hand, then your matrix become a diagonal matrix. Okay. And yeah, so that's why it's called unitary diagonalizable, because A can be diagonalized by this unitary matrix U. And also there are some nice thing you can know, nice connection between this U and D and your eigenvalue and eigenvectors. And yeah, so U is actually composed of the eigenvectors of A. So A has those, I guess here is while writing in a bit of sloppy, because there is something to deal with in terms of degeneracy. But ignoring that for now, so we're starting with unitary diagonalizable. We have a set of orthonormal, bases as orthonormal bases formed by those eigenvectors. Okay, and so that orthonormal basis will be your unitary U here. So if your lambda 1, lambda 2, etc. are your orthonormal eigenvectors, then you just listing them as a column vector, as the column vectors of this matrix, then it will become this unitary matrix U. And the diagonals, then the diagonal elements of this diagonal matrix D will be the corresponding eigenvalues. So you have lambda 1 here, and lambda 1 vector here, and you have lambda 1 eigenvalue here, and lambda 2 vector as the second column, you have lambda 2 value as the second diagonal, etc. Okay, so this is a nice thing about unitary diagonalizable, and its a connection to eigenvalues and eigenvectors. Any question? I think you might already seen this in linear algebra course, but in terms of real value, then you will have also orthogonal matrix and a diagonal matrix, etc. Okay, and if okay, then let's talk about more matrix. We have Hermitian matrix. Okay, Hermitian matrix is it's a lot like a symmetric matrix, but in terms of complex. And it's a matrix where you do this dagger operation, then you still get back to the same matrix. And here is the example. So Hermitian matrix A, you have this 1, 1 minus I, 1 plus I, and 2. And if you do dagger operation, then you do dagger operation, then you transpose and do complex conjugate. I guess we can write down A transpose here for a bit of a comparison. So A transpose equal to 1, 1 minus I, and 1 plus I, and 2. And yeah, and then we do complex conjugation on this thing. Then you see this 1 plus I turn back to 1 minus I, and 1 minus I turn back to 1 plus I. And so I guess from this example, you can see a bit of property of a Hermitian matrix. So its diagonal elements are real because you don't transpose them, and they should equal to their own complex conjugate. Diagonal are real, and of diagonals are complex conjugation to each other. So this 1 minus I is complex conjugation to 1 plus I of diagonals. Complex conjugation pairs. Okay, so this is Hermitian, and also from this thing you should be easy to see that if a matrix is Hermitian, it is normal. Okay. I guess it's not really a quadrant, but yeah, it's like a quiz you can think about yourself. Very easy to see that if a matrix is Hermitian, then the matrix is normal. Okay, a bit here, and anyway, then here we have that matrix is Hermitian if only if it's unitary diagonalizable and all of its eigenvalues are real. Okay. And we already see that why it's diagonalizable because you can show that it's normal, and then if you work a bit harder, then you can see that all its eigenvalues will be real. Okay, let's skip the proof here, and then we have the last property of matrix we want to talk about is we are doing a bit of weird order. Okay, sorry. Actually, we have 2 more, but second last is this positive matrix. Okay. And matrix is positive is we have this not so intuitive definition, but if we sandwich any vector on this matrix, then we'll get a positive value. Then this matrix is called positive. And why this is called positive is that you can show that matrix, if a matrix satisfies this equation, then once again it's unitarily diagonalizable, and all the eigenvalues are positive. Yeah, and that's why it's called a positive matrix, because all the eigenvalues will be positive. And then we have a similar definition that actually we use more is positive semi-definite. And this just means that instead of greater than 0, we have greater or equal to 0 here. Yeah. Okay, so sandwiching with any vector, you get greater or equal to 0. And very similarly, matrix is matrix is PSD if only if all the eigenvalues are non-negative, so greater or equal to 0. Okay. And we'll use this PSD property quite a bit in this course. And PSD is shorthand for positive semi-definite. Okay. And also here we have a small note here because it's a bit confusing. So we have a different notation to the textbook Nielsen and Chuang. Nielsen and Chuang actually call PSD matrix positive matrix. So this is a small difference, but still is a different notation. And I think PSD is actually more standard. Calling them PSD matrix is actually more standard in the literature now, so we'll use the PSD notation instead of just saying this is positive. Okay, and here we have property of matrices that we should do a little later, so sorry for mixing out the order, because we have one more property to talk about. They are projectors. Okay. And projectors are matrices. Here we have a very mathematical notation, a matrix that has p squared equal to p. Okay. And so that's the definition of projector. But actually, this definition is a bit too loose because being a projector don't guarantee you are unitary diagonalizable. Okay, and that's a bit annoying to us. And so in this course, usually when we say projector, we are actually talking about Hermitian projectors. Okay, so you are both this projector P is both a Hermitian and satisfies this equation. It's a Hermitian projector, and because it's a Hermitian, it's also unitary diagonalizable. And then it has a nice property. The nice property is that its eigenvalues will be just two possible value. Its eigenvalue will be either 0 or 1. And that's because if you are a Hermitian projector, so here we have a bit of a proof, then it's unitary diagonalizable, so you can write in U du dagger. Then you think about what's p squared. Okay. And p squared will be du du dagger times u du dagger. But this u dagger and u will cancel each other because they are unitary. And so p squared will be u times d squared times u dagger. Oh, I guess we skip extra step. And also d times d, never mind. Yeah, d times d is d squared. And then this thing equal to p, which also equal to u du dagger. And then you can cancel the u and the u dagger on both sides. And then this thing this give us this equation at the end. So we'll get that d equal to d squared. Okay. But you think about what d squared, d is a diagonal matrix. Then d squared is just basically the same diagonal matrix with all the diagonals being squared. Right? Because you multiply a diagonal matrix, you just multiplying a diagonal together. I guess let's write down somewhere. Like here, we are a little out of space here. So d squared, it will just be, think about multiplication a little, will just be this lambda 1 squared, lambda 2 squared, matrix and all 0 otherwhere. Okay? And so this tells us that every lambda satisfies that lambda squared equal to lambda. And then from this equation, there are only two solutions. It's either lambda equal to 0, so then you have 0 squared equal to 0, or lambda equal to 1, you have 1 squared equal to 1. Okay, and so that's projectors or Hermitian projectors. And example of projector is that is this identity matrix that we like a lot. This 1 0 0 1 matrix is a projector, and you can check that identity square equal to identity. Okay. And also a nice thing about projector is we like to write it as this form. Okay, so we like to write projectors in this bracket notation like this. So it's a sum of those some vector, so it's eigenvector I, ket of eigenvector I, and bra of eigenvector I. Okay. And basically this is just a unitary diagonalizable notation we write, right? Because we say unitary diagonalizable, we have a equal to some I lambda I, right? And now we know the lambda I are either 0 or 1. So if A is a projector, I guess I should have P here. It will be a little clear. So P equal to some I lambda I, and lambda is either 0 or 1. So you can just cross out the 0 part. And so here we are just summing over the non-zero part of lambda I, and the P will be just summing over non-zero part of those I. Okay. And an interesting thing to know is that actually every this eyebrow, eye-cat and eyebrow is also a projector. Okay, and as an example here, so let's go back to this identity matrix. This 1001 is actually a projector onto this 0 cat plus a projector onto this 1 cat because it has eigenvector that's this 0 cat and the eigenvector of this 1 cat. And yeah, it is 0 cat times this 0 bra and this 1 cat times this 1 bra. And yeah, you can easily check that back to here for OI, for all, I guess for all vector V, and V is a one-dimensional projector. Okay. And yeah, we are going over a little. Oh, never mind. We have still have 10 minutes. Okay, and where we start? Wait, sorry. Yeah, we should stop now, right? So let's take a 10-minute break. Okay.先不要，我现在在录音。我们结束再讲。
不好意思，
怎样？
因为我不小心按到选课，就是老师的选课也，就是
应该，
然后所以他加签没有过，所以可能要跟老师再用。
加签没有过哦。就是
我在选课的时候按
错了吗？
又按了你的选课，然后所以他可能加签的时候判定是重堂，所以。
判定重堂 ，OK。不知道，我今天下午有重新同意一次，我不知道有没有签到你。
对，就没有成功。没有成功。再请老师帮我看一次。
哦，好，那我可能今天晚上或者明天再看看。好。
好。
我看一下，有胡子吗？Hello. Okay, let's go back. So we just talked about this one-dimensional projector. So this KV Bravi is we'll keep now start from now on. We'll talk about this as a projector onto V because they are exactly a one-dimensional projector onto this vector V. And I guess this is also a nice example as the outer product. This is the outer product of V with itself. And this is usually how we see our outer product in this course. Okay. And anyway, so we see that projectors can can always be written as this some I and projector onto I. And now let's talk a bit more about linear algebra and geometry. So a bit of a geometric interpretation of projectors. So why are they called projectors? Because if we have some W as a subspace of some space V. So I guess let's see a picture first. So if we have some vector space V, and here with this drawing, V is a three-dimensional space, and some subspace W of this V. So here we have a two-dimensional subspace of V, big V W, and then we have also have W dual here. So W dual is whatever space that's also belongs to W. Okay? So here we have a three-dimensional V, two-dimensional W, and one-dimensional W dual. And the projector is a matrix that will project any vector onto this subspace W. So we have any vector V in this vector space V. Then we'll apply P on it. Then is a P associated with W. Then we'll project this vector V onto this space W. So we have P of V here. And then we can also have another projector, that's Q. That's a projector onto the dual, I guess not dual subspace, sorry, the complement subspace W dual. Okay, so you apply Q on V, then you will become this vector. And also Q will just be one identity minus P. Okay, so that's back here. So so be more mixed. So we have W and V, and then we can find some orthogonal basis for W and some orthogonal basis for V, where this basis is the extension of this basis. So the first K element is the same first K element here, and then you can write down the projector for W easy just from this orthogonal basis. If you just write down sum of projector onto each basis element, this will become a projector onto W. And then you can have this Q, as we say, Q just one identity minus P, and will be the projector onto this W perpendicular, the orthogonal complement of W. And also it's easy to check that Q we can also write in this form is a summation. Those are I projector and I from K plus 1 to D. Okay, and I guess a little bit extra, you might say there are many different orthogonal bases for W, and indeed you can choose different bases here, but if you choose different bases and you sum together the basis element, then you will, in the end you will get the same projector matrix P. Okay. So actually the projector matrix for each subspace is unique. Although the orthogonal basis there are infinitely many choices. Okay, So this is a projector. It's a very geometric object. It projects a vector onto your subspace. Okay. And now let's go back to this property or matrices table. So we have a whole bunch of property. We have Hermitian, positive dependent, positive semi-definite, unitary, and projective. And the definitions are here. So Hermitian means A dagger equal to A. And positive definite means that you sandwich with any vector is positive. And PSD means that you sandwich with any vector that is greater or equal to 0. And the unitary means A dagger times A become identity. And the projective means A squared equal to A. And then we can actually characterize all those properties by just saying they are unitary diagonalizable and with certain properties on the eigenvalues. So Hermitian means eigenvalues are real, and positive definite means eigenvalues are positive, and positive semi-definite means eigenvalues are positive semi-definite, so greater or equal to 0. And the unitary means that the norm of eigenvalue equal to 1. So means that you can be 1 minus 1 or I or anywhere and go e to the I theta. And the projective means that the eigenvalue is either 0 or 1. Okay. Any more question? If not, then let's go a bit more notation. So those notation that we'll use quite a bit in quantum computing. I guess the first one is more quantum computing one is also normal basis, computational basis or standard basis. Okay, so if we have an n-dimensional space, n-dimensional space, then the simplest basis, we call it a standard basis or computational basis, and it's a basis where the basis element are those 1, 0, 0, 0, 0 or 0, 1, 0, 0, 0 or 0, 0, 0, 1. Those are vectors, and we give them the simplest possible notation. So they are just called 0 ket, 1 ket, all the way to n minus 1 ket. And from here you see that we count from 0. Okay, and so for example, when n equal to 2. We already see this a bit before, so when n equal to 2, then 0 ket is 1, 0, and 1 ket is 0, 1. So I guess here we can write down example n equal to 2, and that's when we have a qubit, then 0 ket equal to 1, 0, and 1 ket equal to 0, 1. Okay, and yeah, so but for those of you who have computer science background, you probably know that there is this how to decide notation convention where you want to count from 0 or you want to count from 1. Okay, so with this notation we'll count from 0, so we're counting from 0 to n minus 1. But sometimes we will be sloppy and we'll start counting from 1 to n. Okay. So just hopefully you don't get too confused, and most of the time we count from 0 to n minus 1. Okay, and then another notation, I guess this is not really quantum computing, but we'll use a lot in this course, is and it's not even linear algebra, but anyway we have this delta function notation, so delta jk. And delta jk is a function, basically it's a function of two input of j and k, and j and k are usually positive integers, and delta jk will be 1 if j equal to k, and 0 if j not equal to k. And why do we see this a lot is you can use this notation to express inner product between orthonormal bases, right? Because for example, if you have a set of okay, so say we have if we have j and k from computational basis, if j, let's say jk computational computational is too short here. Okay, so JK is something from here. Then we will have this J inner product with K will equal to delta JK. Okay, so you see you have the inner product between orthogonal basis element. It will become this delta function because each of those vectors, the inner product with itself is equal to 1. When J equals to K, it is equal to 1. And when J not equal to K, then the inner product, they are orthogonal to each other, so the inner product will become 0. Okay? So this is a nice notation you can have, this delta function JK. And I guess let's try a little more. So what you like the delta function most is that let's say you have usually you have a delta function, you also have a summation. So say you have so a lot of things we will do with delta function is sorry, we have a technical issue here. This is very annoying. So summation, usually you have a summation J and some delta function of JK and some function on K. Okay, and then this thing is function on J. Okay, some function on J. Then this thing is just f of K. So say if you are fixed K, because if you sum over J, then sum over all parts of J, and you have delta JK here, then all the J that's not equal to K just give you 0 here. So this delta JK will just pick all the J that's equal to K, and so for those f of J, you only have value when J equal to K, so you just get f of K here. Okay, and this is a thing that we did without talking about delta function before. This is where I think when we talk about eigenvalue, it's a bit of before. Okay, so that is what happened here. So here we have I and J equal to delta IJ, and we sum over I, then this I become J, and this lambda I become lambda J. Okay, so so from now on we can do this with delta function. Sorry, where am I? Oh, sorry. Like about here. Okay, and yeah, so that's computational basis and delta function. And I guess last operation we want to talk about is this trace operation. It will be used some point. Anyway, so trace in terms of operation is pretty easy. So it's some way to calculate the number out of matrix, that the square matrix is you just sum all the diagonal element. Okay, and I guess let's see an example here. It's probably easiest. So we have some matrix 1, 2, 3, 4, and what we mean by trace A is we sum its diagonal element. So we add this 1 and this 4 and it becomes 5. So trace A equal to 5. Okay, I think it is pretty straightforward. And then we can start doing more notation. So in terms of Dirac notation, we can have trace A equal to sum I, and a way to get the diagonal element is to sandwich A with the standard basis, the computational basis element. Okay, so you sandwich A with all the possible I. Okay, I being computational basis, and then you see that this sandwich A with I will just give you the i's element of A. So for example, you sandwich A with K0, K0, you will get this 1. You sandwich A with K1, K1, will get this 4. Okay, and so this notation here, because of this, then it's also equal to just sum I, I. So all the diagonal element. Okay, so the definition here should be simple. And then we have some nice property of trace. So first is linear. So trace A plus B equal to trace A plus trace B. And trace some number times A equal to that number times trace A. Okay. And then we have this most important property of trace that's very nice is that trace AP equal to trace BA. Okay, and so this is called the cyclic property of trace. Okay, cyclic. And why is this very useful is that we can do all sort of weird manipulation. For example, you have a trace A times ket psi times bra psi. Then you can use this property where so we need to have A and B. So we take this part as A, these two matrices multiplying together as A and this as B. And then because of the cyclic property, and why is this called cyclic? Because you can think about you move this B matrix from the end to the beginning. Okay, so you cycle this base matrix B to the front, then you have trace of bra psi times A times ket psi. Okay, and okay. And something crazy about this property is that you see that here is trace AP equal to trace BA. Okay, so trace need to have this A as a square matrix, but this AP and BA here don't need to be square. Okay, so I guess I should note here A, B don't need to be square matrix. They just need to be any matrix. Okay, and that's why we can have this very weird operation where we cycle this this bra psi to the front, and we have a trace of this bra psi and square matrix A and ket psi. Okay. And why this is really funny is because now this is just a number because we are cycling a non-square matrix. We change the dimension of this matrix here. Okay, so now this is, as we said in this class, this is a bracket of something and this is just a number. And you don't really need to do a trace of a number because a number, there is just one number. It's a 1 by 1 matrix. So this is just this number here. Okay, so you see that the cyclic property gives us a very easy way to calculate the trace of this weird object. It's just A sandwiching with this psi. And here we can have more direct proof of this fact by just writing out everything basis elements. Okay, but yeah, this is a cyclic property, and I guess let's talk a little more here. Also, be careful about the cyclic property. It's things like so AB to BA, things like you can reverse the order, but really it's a cyclic, you cannot totally reverse the order. So say you have a 3 matrix, you have a trace ABC, then by the cyclic property you can do this cycling, so you can is equal to trace CBA. Not CBA, that's wrong. It's equal to trace CAB. So you can move C to the front, but this is not necessarily equal to trace, say you reverse the order, CBA. Okay, because you can only cycle this around. Okay, so you can do one more cycle, so you can move B to front. You can have trace BCA. Okay, but you see that if only do this cycling, you can only get these 3 combination, and you cannot get like a CBA or ACBA, etc. Okay, so be a little careful about this cycling property, cyclic property of trace. And yeah, so that's all the operation I want to talk about for now. Any question? If not, then let's go to things that you really need to memorize, and but they are related to content computation. So there are some 2-dimensional metrics that are very important to content computation. They are called Pauli matrices. They are named after Pauli, that's a physicist. Okay, and Pauli matrices, they have many different names. and we will mix the notation in the class. And I think the simplest notation for that is are those big X, big Y, and big Z. Okay? And but as I said, there are many names for them. They are sometimes also called sigma X, sigma Y, sigma Z, or sigma 1, sigma 2, sigma 3 when you want to just count from 1 to 3. Yeah. And yeah, those three metrics, and there are three very specific metrics, and you should memorize what they are. And X is 0, 1, 1, 0. And Y is 0 minus I 0, and Z is 1, 0, 0 minus 1. Okay, those are three Pauli matrices. And yeah, I guess usually I think X and Z are a bit more symmetric and easy to remember. And Y, it has this weird sign. Sometimes you forgot where the minus sign is, negative sign is. And funny way to memorize is remember that if you think a negative sign makes things kind of lighter weight, and then you think negative sign is on the upper side because they have lighter weight and they float up. Okay, so this is a bit of a joke on how to memorize sigma Y. Anyway, those are our three Pauli matrices: sigma X, sigma Y, and sigma Z. And they are very nice matrices because first you can see they have two properties. They are matrices that are both unitary and Hermitian. You can just check it yourself. They are both unitary and Hermitian, and that means that their eigenvalues are 1 and minus 1. Yeah. And then there is also this Hedman matrix that's also unitary and Hermitian, and you also memorize it. It's 1 over square root 2, 1, 1, 1 minus 1. Okay. And I guess a bit of intuition about those four matrices. And so X and Y and Z will actually kind of corresponding to, I guess we're going back a bit of physics, but it will actually corresponding to x-axis and the y-axis and the z-axis in actually three-dimensional physical space. And yeah, we'll talk a little bit about it later on in the class. Okay, but sometimes you can think about XYZ corresponding to the x direction, y direction, and the z direction of our three-dimensional space. And that's when we are operating on a qubit. You can see those are all two-dimensional vectors because it will be operated on a qubit, which is a two-dimensional space. And Hedman matrix we will see very soon that is really nice because it relates the X matrix, the X Pauli with the Z Pauli. Okay, and anyway, let's back to seeing the property of Paulis. So first, nice thing about the thing we should also memorize quite a bit is the eigenvectors and eigenvalues of Pauli matrices. Okay. And the eigenvectors of Z matrix are just the computational basis vectors, so most simplest possible vector, because you see Z is already diagonalized. So the eigenvector of them is just 1, 0 of it is just 1, 0 and 0, 1. And yeah, so multiplying 1, 0 on Z, you go back to 1, 0. So you have this 0 cat as one as the eigenvector of Z with eigenvalue 1. And then this 1 cat, which is 0, 1, is also an eigenvector of Z with eigenvalue minus 1. Okay. And then we also have the eigenvector of X, which you should also memorize. Those two vectors are very important. And we just define it as this 1 over square root 2 times 1, 1 vector. And 1 over square root 2 times 1 minus 1 vector. And you can easily check just by doing matrix multiplication. You multiply 1, 1 and then 1 minus 1 on this matrix. You see that you get back 1, 1 on it, you go back to 1, 1. And 1 minus 1 multiplying with x, you go back to 1 minus 1, but with a minus sign. And I guess we can have a bit of interpretation here. So this x matrix, you actually swap the two coefficients of whatever vector you multiplying on it. So what I mean is that so if you have this 0, 1, 1, 0 matrix, this is x, multiplying on any vector AB, then this actually becomes the vector BA. So you swap the two coordinates. Okay, so yeah, you just multiply and you see that this become B, this become A. And so you can kind of see why these two are the eigenvectors of x, because if you swap 1, 1, then nothing happens, you still get 1, 1. And if you swap 1 minus 1, then you get a minus 1, 1, which is a negative sign on this 1 minus 1. Okay? And yeah, it's also a bit nice to remember that x has this swapping property. Okay? And we like, so those three matrices are polymatrices. They are kind of equally important to each other, but usually people like X matrix and Z matrix more. And it's partly because they are real matrices, and real matrices are easier to deal with. Okay, so it's more important to memorize these 0, 1, they are eigenvectors, these 0, 1, and plus minus. But nonetheless, we can still have the eigenvectors for y. And you can kind of see why it's less loved here, because their names are more generic. So the eigenvector of y is just called, they don't like it. Unlike eigenvector of x and z, you have this special name plus and minus. It's just called y plus and y minus. For eigenvector of y with plus 1 eigenvalue, and the eigenvector of y with negative 1 eigenvalue. And anyway, you see eigenvector of y are also more complicated. It has this complex value, and if calculated out, it is 1 over square root 2 with 1i, and 1 over square root 2 with 1 minus i. Okay, and yeah, although we will not use them so much, it's also nice to know those two are the eigenvector of y. Okay, so those are about the eigenvector and eigenvalue of x, y, z. Any question? If not, then let's talk about Hedema. Okay, and the most important thing about Hedema is that it swaps x and z. And what we mean is that basically those two properties, they are kind of the same property, but anyway, let's listen out. So if you apply Hedema on 0 on the eigenvector of z, it becomes eigenvector of x with the same eigenvalue. So Hedema on 0 become plus, Hedema on 1 become minus, and Hedema on plus become 0, Hedema on minus become 1. Okay? So you swap the x and z. And also you can swap the x matrix and the z matrix directly with Hedema, and you have Hedema, if you sandwich z with Hedema matrix, it becomes x. If you sandwich x with Hedema matrix, you become z matrix. Yeah. And also a property that you might already infer from here is that Hedema squared become identity. So you apply Hedema twice, just back to identity matrix, that's nothing happened. Okay, so that's the most basic properties of polys and Hedema, and let's have more properties of polys. Okay, and I think a lot of property of poly come from that the eigenvalues are polys and Hedemas are that their eigenvalues are 1 and minus 1. Okay, and from here you can derive several properties. So for example, the square should become identity, because you take a square of a unitary diagonalizable matrix, then you square the eigenvalue, and the square of those eigenvalues are identity. So yeah, the sigma square also always become identity. And also the determinant will be the product of the eigenvalues, so it's minus 1. And the trace, we didn't quite talk about this, but the trace will be I guess we can prove this very quickly here. So the trace will be the sum of eigenvalues, and that can come from just the cyclic property. So trace of A equal to, if A is unitary diagonalizable, trace of U du dagger for some unitary U and a diagonal D, and I should plug in power now. Yeah. and 帮忙一下。介绍它们。Sorry for the interruption. So A is unitary diagonalizable, so it's trace U du dagger, and then we can use our cyclic property to move this U dagger to the front. So U dagger U D, and we know U dagger U is identity, so this is just equal to trace D. Okay. And but D is just a list of eigenvalues, so trace of it is a sum of eigenvalues. Okay. So trace of a matrix is a sum of its eigenvalues. And then go back to our polys. The eigenvalues are 1 and -1, and you add them together, it becomes 0. Okay. So you can derive a whole bunch of property from just the fact that the eigenvalues are 1 and -1. Okay. And the more important property that I guess used quite a lot in physics, but we use only a little bit, is that the polys are anti-commutable. Or I guess the mathematical term here is that they form an algebra. Means that if you multiply two poly together, you get the third poly. Okay, so just those three equations we show here. So xy equal to I times z, and yz equal to ix, and zx equal to iy. Okay, so you multiply two poly, it becomes the third poly with extra I here. Okay, you can just check it yourself. And I guess I should erase this thing. Anyway, x, y, y, z, z, x. Yeah. Okay, and the next property is also very important in terms of physics, and I guess nice for you to very nice for you to do calculation, is that polys are anti-commute with each other. Means that xy and yx are different by a negative sign. So xy equal to yx, and similarly yz equal to minus zy, and zx equal to minus xz. Okay. So so the product of two different polys has those nice properties. Okay. And from this thing and this thing, and from the thing we said, so I guess from this one and this one and this one, we can get the nice property of polys being kind of like a basis. Okay, we can think of poly as a this thing and this thing. Okay, although polys are matrices, but we can think of matrices. How do I say? We can have a linear subspace spanned by matrices also, and polys are kind of orthogonal to each other in terms of this weird relationship. Okay. And the relationship is that we have a kind of orthogonal relationship between different polys, such that if you multiply two polys together, here ij are anything from 1 to 3, then you multiply sigma and sigma j and take the trace. So you can think of this as the inner product between different polys. Then they become like a delta function with HR2 in front. Okay. And how we get this is that we can check two different cases. So if I not equal to j, then we should get 0 here. And I not equal to j, why is this 0? Is because I not equal to j. Then sigma I times sigma j is one of these. It's some number times the third poly, so sigma k. Okay, and then let's say, for example, you have sigma I sigma j equal to xy. Then you have this equal to iz, but then we know trace z equal to 0, so the trace is 0. Okay. So if you have sigma I, sigma j here, then basically you have some number times sigma k. Then trace sigma k equals 0, so you got 0. And when I equal to j, then we have that for every I, sigma I squared equals identity. Then we have a trace of identity matrix, which will just be 2, because we are in 2 dimensions. Okay, so we see that the polys has this kind of orthogonal relationship, and we will actually be more explicit about this now. But we see that the polys are basis for two-dimensional matrices. Okay, so yeah, not quite, but yeah, we'll see that later. Okay, and for now, it's nice to know that this property exists and know its derivation. Okay, and now we have so those are about polys, and we have one more notation that's we will not use too much, but it's nice to know because you will see that here and there in different quantum computing literature. Those are commutators, and they are I guess they are more like abstract algebra concepts. But anyway, they are quite related to polys because polys has nice commutators. And what are commutators? They are just something you can calculate from two matrices. So you have A and B being any two square matrix. Then you can have a commutator that's just A times B minus B times A. Okay, and basic commutator calculate how much matrix commute. So I guess the idea is that you want to see how much the two matrix commute. So if the two matrix commute means AB equal to BA, if AB equal to BA, then you have this commutator between A and B equal to 0 because you have AB minus BA equal to 0. Okay? So commutator is a way to calculate how much your two matrix commute. And anyway, if you have, you can have a commutator between two poly, and you will become the third poly. You see that it has some nice connection to poly. So for example, XY commutator is Z poly. Okay, and also you have the anti-commutator. Calculate how much your two matrix anti-commute. So you have anti-commutator between A and B being just AB plus BA. And here we have that any two different poly will anti-commute with each other because sigma I, sigma j anti-commutator is 0 if I not equal to j. For example, this xy anti-commutator equal to 0. And this comes from this thing because we have xy equal to minus yx. And so you add those two things together, it becomes 0. You add those two things together, it becomes 0. And you add those two things together, it becomes 0. Okay? So poly is the anti-commute. And the anti-commutator is the other poly. Okay? And okay, that's all I want to talk about polys. And let's see. Then we have the last mathematical concept, but I don't really think we can do this in 10 minutes. But let's try to start this a little bit. Okay, so now this is a thing that you probably really didn't hear about. It's a tensor product. It's a product usually taught in linear algebra course, but this is an essential part of quantum computing. And the definition here we give is a tensor product is a product between any two matrices of any size. So we can have a matrix A with dimension n by n, and a matrix B, excuse me, with dimension p by q, and you can just define a matrix that's A tensor B, and it's a really huge matrix. It's m times p by n times q matrix. Okay, so it's basically a product on everything. The product of its number of rows is the product of this n and p, and the number of number of rows, and the number of columns is the product of this n and q. And what does this matrix look like is this. Okay, so I guess this notation is okay. Okay, so it's a lot of block matrix placing together. So you have a whole bunch of B matrix here, and each one of them is multiplied by a coefficient of A. So remember, A is n by n matrix, so A is from this A11 to AN1, and this A1n all the way to ANN. Okay, so all those Aij is a number, it's the individual element of A. Okay, so that's right here. So A equal to A11 and A21 to AN1 and A1n to AMN. Okay, so yeah, this is a huge matrix. So you have a whole bunch of B multiplying with the coefficient of A and place them all in this huge matrix. Okay, this is a definition. Okay, and if you just want definition, then this slide have everything. But obviously there are a lot of ideas associated with this tensor product. Okay? So the idea of a tensor product is that like holding different slots for matrix arithmetic. And what we mean is that we have this nice property from the definition of tensor product. So if you have A tensor B, so this is a big matrix, and some C tensor D, and with C has the same dimension as A, and the D has the same dimension as B, so that they all fit together. Then these two huge matrices multiplying together is equal to you just multiplying the first slot together, so A multiplies C, then tensor with B multiplied with D. Okay. So I think this is the most important with property with tensor product is that you can keep these different slots such that when you multiply different tensor product, you are just multiplying different slots. I guess I talk a little too strict, and here this property actually is stronger than it seems. So actually A don't need to have slightly correction. So C don't have the same dimension with A. So C need to have dimension such that AC exists, and D need to have a dimension such that BD exists. So like I think the second dimension with B should be the same as the first dimension with D. And the second dimension with A should be same as the first dimension with C. And I guess let's see some example first. Okay, so tensor product, because we defined our matrices, you can also work on vectors. And actually a lot of tensor product we do is on vectors. So for example, we have this psi vector and the phi vector. then we can take a tensor product with between them. So we have those block with of 5 vectors. So this 3, 4, we have 3, 4 here, 3, 4 here, and then we have psi equal to 1, 2. So first block of 3, 4 is multiplied by this 1, and the second block of this 3, 4 is multiplied with these 2. Then we get this huge vector that's 3, 4, 6, 8. Okay. And then we have an example of 2 actual matrices. So we have 1, 2, 3, 4, and 5, 6, 7, 8. Then we have 4 by 4 4 by 4 block here. So we have a 4 block of 2 by 2 matrix. So we have 5, 6, 7, 8 here, and this is multiplying by 1, then multiplying by 2, then multiply by 3, and then multiply by 4. Okay. And yeah. Okay, so this is a tensor product, and so tensor product give us matrices. They are huge matrices, and they have this nice rule. And another thing we can do with tensor product is, well, since it's a matrix, then we can we can have a linear combination of different tensor product because we are just adding matrices. For example, we have 1, 2 tensor product with 3, 4, and 1, 1 tensor product with 1, 1, and 1, 1 tensor product with 1, 1 is just 1, 0, 0, 0. And those two are matrices, and they have same dimension, and we can just add them together. So we can add them together and then become this huge matrix or a huge vector. Okay. And I think we can actually finish most of it, but anyway, next time we'll try to see how much we can get. Okay. And then we have more notation. So in particular, when we have tensor product for different vectors, then then we have different shorthand notation. So the most standard notation is I guess the most complete notation is psi tensor product with phi. And but people get lazy over time, so then you will start by omitting the tensor product here, then just write the ket psi ket phi, and up until here it's not very ambiguous because there is no other product of 2 vectors of a 2 column vector like this. And then we get more lazy, and then we omit the middle part. We just write a comma here. We have a psi comma phi, and then people get even more lazy. You will get just ket psi phi, and this is a bit troublesome because yeah, this is a bit troublesome because this might mean different things. But anyway, we'll see this. And so, for example, sometimes people write 0 ket tensor 0 ket as 0, 0, something like this. And somehow this notation is actually not ambiguous because how we count the bit strings. But anyway, so things like this will happen. And then I guess this is okay-ish simplification, and there are very bad simplification is when people also do similar thing to matrices, then it's really troublesome. So you should write a tensor B, but sometimes people just write, I guess if you just AB is not so obvious, but sometimes a lot of time you will want to write some polymatrix X tensor Y, and tensor a lot of polymatrix, but people get lazy and they just write X Y. And now it's really ambiguous. You don't know it's X tensor Y or it's X multiplying on Y. And yeah, then it's something you need to learn from context. But anyway, we're over time, so we will stop here. And yeah, and we will kind of jump over a little property of tensor product, and we'll stop here, and we'll see you next Tuesday. Okay.